So what do we do if we are trying to evaluate the limit as x goes to c of f of x if c is not in the domain of f of x? That is, we sit down and we try to just plug c into f of x, and we run into a problem because we're either dividing by 0, taking a square root of a negative number, something like that. Well, one method is to use algebraic manipulation. For example, factoring, expanding, or rationalizing, e.g. rationalizing a denominator or numerator, to replace f of x with a function g of x that is actually defined at c. And so long as g of x is polynomial, rational, algebraic, then we can just plug in. And then we use the fact that if f and g are two functions that are equal to each other for values of x that are close to but not equal to c, their limits as x approaches c are equal to each other. Let's work through an example. So let's evaluate the limit as x approaches 1 of x squared minus 1 over x minus 1. Let's note that if we were to just plug in x equal to 1 into this expression, we would get 1 squared minus 1 over 1 minus 1, which is 0 over 0. So first of all, 1 is not in the domain of this expression. Second of all, however, these are two polynomials, both of which are equal to 0 when I plug in 1. That suggests that they have a common factor and that I should be able to cancel that out. So there's really only one way to go here, which is to factor. We're going to factor the top and bottom. Well, the bottom is already factored. It's a linear expression, so there's nothing to do. The top is x squared minus 1, which is a difference of squares. So we get x minus 1 times x plus 1 over x minus 1. Well, that's what we expect. We expect there to be a common factor of x minus 1 because both of these polynomials are equal to 0 at 1. So we can cancel them out, and we're just left with the limit as x approaches 1 of x plus 1. Now, x squared minus 1 over x minus 1 and x plus 1 are two different functions. However, they are equal to each other so long as x is not equal to 1. So we're using the fact that if I can replace the function which behaves badly at 1 with a function which behaves well at 1, then I can evaluate the limit by doing that. I just take x equal to 1, plug it into x plus 1, and I get 2. So I would like you to try something very similar. Question number 2 is for you to evaluate the limit as x approaches 2 of x minus 2 over x squared minus x minus 2. Okay, now let's evaluate the limit as h approaches 0 of 2 plus h squared minus 4 over h. This looks like the difference quotient example that we looked at on the very first day that we actually did problems in class. This is going to be an expression that we'll see a lot when we're trying to evaluate derivatives straight from the definition. Now, if I just plug in h equal to 0, I get 0 over 0. Just go through the math. That suggests that there's a common factor. However, the bottom is just h, so the common factor on top itself should also be h. I don't see a common factor of h on top. That's because it is not simplified. So the first thing that I'm going to have to do this time is to expand the top, expand the numerator. So I do that. I take 2 plus h and I square it out using a squaring formula, giving me the limit as h approaches 0 of 4 plus 4h plus h squared minus 4 over h. 4 and 4 and negative 4 cancel out to leave me with 4h plus h squared over h. And now I can factor. Now I see my common factor of h. I factor an h out on top, leaving me with 4 plus h times h. Now the h in the denominator and the h in the factor of h in the numerator cancel out. I'm left with the limit as h approaches 0 of 4 plus h. Now I can just plug in h equal to 0 because this is now just a polynomial, and I get 4. So this time we had to both expand the numerator and then factor and cancel. Now let's do an example where we have to rationalize, and these are really the three basic things we expect to do in these sorts of problems where we're using algebraic manipulation to evaluate limits. We factor, we simplify by expanding out, and we rationalize. Now I know that I need to rationalize when I have an expression such as this, a square root plus or minus another square root, and in particular, if when I plug in the value of the limit, that square root expression is equal to 0. I've got the square root of t squared plus 9 minus 3 over t squared. If I plug in 0 into the top, I get root 9 minus 3, I get 0. The bottom is also 0, so I'm going to expect some sort of cancellation after I factor. But the top, there's no clear way of factoring it because it's some sort of weird square root expression. The way that we manipulate a square root expression so as to be able to factor something out of it is to rationalize the expression. Here I'm going to rationalize the numerator because that's where this square root expression is. So to do that, I'm going to multiply the top and the bottom by the conjugate of the top. I have the square root of t squared plus 9 minus 3. I replace the minus with a plus to obtain the square root of t squared plus 9 plus 3. And I'll multiply the top and bottom by this. So that's what I've got going on over here. I'm really just multiplying by 1, so I'm not changing the expression, the value of the expression. But this is going to allow me to get rid of the fact that I've got 0 on top and on bottom when I just plug in t equal to 0. Okay, so when I multiply the numerators, I get the square of the square root of t squared plus 9 minus 3 squared because it's the difference of squares, a minus b times a plus b. The bottom, I just get t squared times the square root of t squared plus 9 plus 3. Now I square at the top, the square root and the square cancel, leaving me with t squared plus 9. 3 squared gives me minus 9. On the bottom, I've got the same thing as I did before. 9 minus 9 is 0, so I'm left with t squared over t squared times the square root of t squared plus 9 plus 3. And I just noticed I'm missing a parenthesis. Great. I can now cancel out these factors of t squared. I expected to have a common factor of t because when I plugged in t equal to 0, I got 0 on top and on bottom. In fact, I'm a little surprised that I got a t squared on top and on bottom to cancel out. What I'm left with is 1 over the square root of t squared plus 9 plus 3. This is a rational function. This is an algebraic function where 0 is actually in the domain. I plug in 0, I get 1 over the square root of 0 squared plus 9 plus 3. I can evaluate that. And at the end of the day, I get 1/6.